It's on DVB IP streaming testbeds for digital media content synchronization. Media content synchronization is basically his field of research. Mr. Kobel graduated from a university here in Germany, in Mittelhessen, and then moved over to Havana in Cuba, where he's currently a PhD student at the Polytechnic University in Havana, working on media synchronization issues. And we will hear about his work in the next presentation. Welcome.
Well, again, thank you for the introduction. My name is Kobel. Today I would like to tell you a little bit what we are doing in synchronization in the research project HBB-NEXT. HBB-NEXT is a project sponsored by the European Community, nested within the FP7 call. And before I start with our demonstrator, I'd like to tell you a little bit about HBB-TV and HBB-NEXT. So I think HBB-TV is a non-standard. This is a currently uprising standard, especially here in Europe. It basically aims to bring together the broadcast world and the broadband world. And the broadcast world offering standard services like DVB streaming, DVB broadcasting, and the internet services like complementary services. In the case of HBB-TV, these are, for example, on-demand videos, or text-based information, and so this is then created and formed for the HBB-TV platform. And HBB-NEXT is something like, well, it's thinking about, okay, what else can we implement in HBB-TV? What does the user want? What possibilities do we have? Taking all technical features of today's networks and hardware into account. And on the right side, you see a lot of features HBB-NEXT is targeting to implement. For example, user recommendations, group awareness, multi-device, and especially, and this is our part, audio-video synchronization of hybrid sources. Hybrid in a meaning that media comes from different sources, technically different sources, and also later on the multi-source content. This is meant here with hybrid content. And so the project started last October, sorry. And right now we currently finished our first demonstrator. We have basically three steps what we want to achieve. First would be the intermediate synchronization, where you have content coming from two different entities in the network, and but they are synchronously played out on a single device. The next step then would be the inter-device synchronization, where you have the same content synchronously played out on different heterogeneous devices like TV screen, a tablet, smartphone, and so on. And the last step we want to achieve is a iframe, synchronous synchronization of the both. So, and now a demonstrator. What do we want to do exactly? We have a German newscast here, and from the internet coming, we have an IP video, which is a sign language interpreter, which of course they belong together. I show you this because at the ARD or RBB booth here at IFA, the front end of this demonstrator is shown. So if you're interested, after this you can have a look. It's in Hall 2. And to get back to the HBB-NEXT architecture, the high-level architecture on synchronization, we want to include all involved components. We have the classical DVB broadcaster. We have third contents or third-party content providers for IP content, and we have the client synchronization, which then brings together and renders both inputs or multiple inputs in a picture-in-picture fashion, for example. By the way, this is running picture-in-picture. And okay, so I mean, I think the problem is generally known. Synchronization within a transport stream in the DVB world is pretty neat. It's working well because it's easy. You can easily synchronize all the elementary streams in a transport stream to each other because they reference to the same clock. They have the same PCR values. But what about IP? So synchronization of the internal transport stream element streams to the outside world is technically a difficult task and also a well-reviewed task in research. So we wanted to see, okay, how can we solve this? And this is our demonstrator. Just to show you the hardware elements, we have a playout center, which represents the DVB broadcaster. We have a web server, and we have a set-top box, but this set-top box is TV-based. The web server, the content there is stored on MPEG-Dash. MPEG-Dash is an adaptive streaming format. I think it was created based on the popularity of standards like HLS from Apple. I mean, it has certain advantages like adaptive streaming, but we want to use it also for synchronization by decreasing the segment size, and then each time we play out the video, the IP video will directly jump to the actual segment. Okay, so what do we basically do? Our implementation or our approach already starts at the broadcaster side by preparing the transport stream. Basically, we take the elementary stream of the video, of the main video stream, and look for iframes, for PES header that contain iframes. If we identify one, we copy the PTS value and put this PTS value in a new packet, which is called a broadcast timeline packet. So this PTS value from a PES packet containing an iframe goes into a new packet. And there's some auxiliary data contained here, but the most important thing is we include an absolute timecode value. And this is an absolute time which refers to the starting point of a DVB event. This needs to be provided, of course. So we do this only for all iframes, and based on this we create a new elementary stream which just contains timeline values. Okay. Now, about the functionality of the demonstrator, let me tell you how this works right now. So we take a regular transport stream, which is our newscast. We load it into an MPEG test system, and first of all, we add stuffing bytes. So why are stuffing bytes important? Because we need now the space of the stuffing packets for our timeline packets. Because the timeline generator then looks for every iframe and then identifies the next or the first stuffing packet behind each iframe and replaces it with the previously created timeline packet. And this is why we need to, in our demonstration, we need to add stuffing bytes. We can say that the more stuffing bytes we add, the more accurate the synchronization will be later onwards, we will see. And then in the last step, we add a custom PID for the PMT, the program map table, so the timeline on the receiver side will be identifiable. And then the output of this is the previous audio-video elementary stream plus the broadcast timeline. And then this is going to the modulator and broadcasted. So just a screenshot how this process of adding stuffing packet works. This is not a big deal. For example, the stuffing packets, they always have the same PID. It's hex 1FFF, and you see, for example, in this example here, we add around, it's this one, we add around 1.3 megabit of stuffing packets, which is, for example, sufficient for our approach to the original transport stream. Okay, and then later on, what you see here, the screenshot, this is happening here in the timeline generator. Right now, it's not doing its work live. It's a program. It's just a program in which we load the original transport stream, and then it replaces, as I said, the stuffing packets with the timeline packets, and then we have some statistics here. For example, for the transport stream, how many iframes were found, is the iframe density sufficient, how many stuffing packets were found, and then it also creates statistics on the distance between an iframe, the distance between an iframe and when the timeline packet comes afterwards. And this distance is in packets. Yeah? We'll see later on in the results. And yeah, this is already what we got so far. What do we see here? We have the same transport stream, and we just wanted to test, okay, how many stuffing packets do we have to add in order to be sufficiently accurate in synchronization? Because the goal is to keep the distance between an iframe and the regarding or related broadcast timeline packet as close as possible or as short as possible. And we see if we add 10 kilobits per second of stuffing packets, the distance over the time, these are the samples here, over the time is pretty high. It goes up to, I don't know, 750 packets between an iframe and the next timeline packets, which is probably too high. And but if you, the more stuffing, the higher is the bitrate of the stuffing packets, the more accurate gets the synchronization. For example, you see here a huge step already between 10 and 50 kilobit, and yeah. If you add 5 megabit extra of stuffing packets, the distance is almost, I guess, always 1. So same graphics, well, the same measurement. Again, the average and the maximum iframe to timeline frame distance. This time here on the x-axis we have the stuffing packet, sorry, the bitrate for the stuffing packet, and we see, okay, for 10 kilobit, the average distance is 320 packets, still pretty high, but this rapidly decreases the more stuffing packets we add. So this is what we wanted to focus first on the broadcaster side. This is what we are currently doing. What do the broadcasters need to do? What do they need to offer in order to include absolute timecode information broadcasted on air? And but what about the client side? The implementation of the client synchronization until now is pretty simple because yeah, it's a low solution complexity. We have a Firefox browser plugin for the front end, for the playout. It's running in the browser, and yeah, the syncing itself is done in embedded JavaScript code, and the playout of the DVB and the IP video is done in direct show, the very common Windows media platform. And yeah, the DVB stream is acting as a master, and the IP video stream is always acting as a slave. So for the IP video stream, we just have 3 operations, which is play, seek, pause, if we want to have the sign language interpreter on demand. And the synchronization right now is pretty easy. It's in Java code. Here we get the broadcast object, which is the DVB stream. Here we get the broadcast. Exactly. And here in the broadcast object, the actual play position, which is the absolute time information, is already included. We get here is the IP video, and then we just say okay, the IP video just jump to the actual broadcast play position, and it's played out synchronously. But the client-side implementation is pretty basic, as you can see, and yeah, this is the next step we want to improve. So as you can see, it's an ongoing project, but I think we can all agree that the necessity for synchronization in the future of hybrid content from hybrid sources is definitely existing, and user demands also a high level of accuracy. And because nothing is more annoying than have a delay between 2 synchronized videos. Yeah, that's about it.
Thank you very much for your quick and very comprehensive talk. Are there any questions from the panel, please?
So you said that if you add more stuffing packets, the synchronization is better. what is the penalty that you pay for adding more?
You lose data rate.
Under, so I
What
can't hear.
is the penalty if you add more study packets?
I mean,
Penalty.
yeah, of course, for the broadcaster it costs money. So the question is, okay, if you have a full transport stream with a lot of services or programs inside, how many stuffing packets are available? This is still up for evaluation, definitely.
And so
I
how
would like to ask a similar kind of question. You showed this graph where we saw that depending on the amount of stuffing packet you would add, the delay would be reduced. But what is the target delay? For example, the signing application, what target delay would you work for?
The target delay, we are targeting 40 milliseconds because this is the based on the frame rate.
There was another question from the page.
Could you comment on why you actually need to add a timeline? Because isn't there actually a timeline?
There's plenty of timing information, but there.
Timing information with the timeline. Actually, the TV shows you at which point in time of the TV show you are period.
Yes, you mean that you could obtain the play position of the actual event on the client side. I'm not quite sure. I think this also implies some technical problems. But right now, I can't tell you the details. I would have to double check. But you're right. Yeah.
My personal estimate would be that this is required by the broadcaster because they want the actual time code of the production tools inside of the studio. So I believe it's more the studio which requires exact time code as usual in the frame consistent time code than the receiver, I guess. All right, thank you again. Thank you.